Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders 2013, problem number 4. Let A be a unital ring in which a squared is not zero for non-zero elements, and let B be the set of all elements such that their square is 1. We have two parts. Part A. We wish to show that AB minus BA equals BAB minus A for all elements A in A and B in set B. And second part, we wish to prove that B is multiplicative group. So B with 1 and with operation of multiplication forms a group. So it's a nice problem from abstract algebra. Here are my hints. First, you should consider this lengthy expression AB minus BA minus BAB plus A, everything squared. You should expand it, cancel a bunch of terms, and you should get your result of part A. And for part B, you should first compute ABAB plus BABA using the result of part A. Then you should show that AB squared equals BAB minus A plus 1, again using part A. And finally, you should simplify AB squared minus 1 squared, where this time both A and B are from set B. So give this problem a try and I will see you in just a minute. Right, so let's start with part A. What I wish to do is to consider AB minus BA minus BAB plus A squared. Well, notice that this is exactly the same as this times itself. Exactly the same. And now, using the distributive law, you should multiply everything by everything. This times that, times that, and so on. Some work needs to be done. I will give you the final result. All of this simplifies to this expression, which you see here. You can verify it yourself. And now, let's use the fact that B is in our set B. Well, since B is in set B, we have, well, B squared is 1. B times B is 1. And let's take a look. Here we have exactly B times B, so it's 1. Likewise, here we have 1, 1, 1, and that's it. 4 times. And now let's do simplifications. Here we have, for example, ABAB, and here we have minus ABAB. All right. Here we have minus A squared, and here we have plus A squared, so it's gone. Here we have AAB, and here we have plus AAB, so it's gone. ABA minus ABA, BAAB, BAAB. Right. What else? BABA, BABA, BABAB minus BABAB, BAA, BAA. Everything is gone. So our result is 0. And now we'll use this crucial property that A squared is not 0 for elements which are not 0. I will call this condition asterisk. By asterisk, since AB minus BA minus BAB plus A squared is 0, we must have AB minus BA minus BAB plus A equals 0. Because if it were not to be 0, then its square also wouldn't be 0. Which means, after taking some elements to the right hand side, i.e. for every element A of A and for every element B of B, AB minus BA equals BAB minus A, which closes the proof of part A. Quite easily done. Right. What about part B? For the part B, we wish to show that B with multiplication is a group. Yes, and to do that, we need to do three things. First, we have to establish that 1 is in B, but it is. Notice that since 1 squared is obviously 1, we have 1 is in B. No problem there. Moreover, let B be in our set B. Notice that then B times B is 1. So the inverse of element B is B itself, which is again in B. So if some element is in B, its inverse is also in B. The last condition is harder to verify. Now let A and B be two elements of B. We wish to show that AB squared is 1, but it needs some work. Now, I will first consider this expression AB. Notice that by part A, BAB can be written as AB minus BA plus A. Alright, so let's write it. This part, I will replace it by AB minus BA plus A. Right. And now let's expand it. It's A squared B minus ABA plus A squared. And now, what is A squared? Well, since A is in B, A squared is 1. So it's B minus ABA plus 1. And now let's compute BABA. Notice that here we have BAB, so it can be replaced once again by part A by this expression, AB minus BA plus A multiplied by A. So it's ABA minus BA squared plus A squared. And what is it? Well, it's ABA minus B plus 1. And notice that if we add these two expressions together, we will get, after addition, we will get that ABAB plus BABA is just 1 plus 1, because this cancels with that and this with that. And remember it. Let's remember it. Now, I wish also, and now I will consider just AB squared minus 1. AB squared minus 1 squared. So it's AB minus 1 quantity squared. Once again, here we have our part BAB. Well, notice that ABAB can be replaced by this, so it's we have already demonstrated that it can be written as B minus ABA plus 1 minus 1 quantity squared. So in other words, it's B minus ABA squared. Alright, and now let's do again the boring stuff, namely multiplication. So it's B squared minus BABA minus ABAB plus ABA ABA. And now let's see what can be done. First of all, B squared is 1. This part right here, we have minus BABA minus ABAB. it has been demonstrated that it can be written as -1, -1. And what about the last part? Notice that here we have AA, it's 1. So then we have BB, it's 1 again. And finally we have AA again, so it's 1 once again. So we have 1, -1, -1, plus 1. So it's 0. It's 0. And once again, we will use our property asterisk by our defining property of our ring. Since this squared is 0, the number inside must be also 0. So AB squared equals 1, i.e. element AB is in our set B, which means that our set B is closed under taking products. It's closed under taking inverses. It has element 1, so it's a subgroup. It's a group. So B with multiplication is a group. And that closes the proof of part B. Again, quite easily done. And that closes our problem. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.